waiting for get to like 199 and and then 200. I don't know that we'll make it all the way to there. I didn't make it quite this far during second. Let's get after it. Now, the thing that I want you to remember is that although I gave you those two different styles, the F's and the G's and the U's and the DFs and the DU's and all that stuff, I think the easiest way to think about the chain rule is inside versus outside. Okay, like what's the big thing happening to something that's just more than X? And fingers crossed, it's just the power rule. Like that's kind of what I'm hoping, is that the big thing that's happening is there's an exponent on the outside, and then everything else is stuck inside. And then I can use the power rule as my style choice of finding this derivative, and then kind of going from there. And what's nice about f of x is it's a really good one to start with because that's what we've got, right? The big thing that's happening is we got something cubed. And so when we take the derivative of that something cubed, I use the power rule first and foremost, but then we'll just multiply by the derivative of the inside as part of that chain. Okay, so f prime of x right away is ready to go. It looks like a power, so I can use the power rule. I've written as a polynomial. Now, hey, if you wanted to cube that, go ahead, go for it. Right? You can always rewrite the function if you can ahead of time and see where it gets you. And f of x could be done. But we saw yesterday that's just more work usually. So here's what I'm going to do, right? The 3 goes in front, multiplies with any coefficient that was there in case there was. Okay, power is going to decrease by 2. And I'm just going to switch colors so you can see kind of how this is going to work out. The inside stays the same. Okay. That's my inside function. Right? Remember, we got composition of functions here. It's not just x cubed, but more than that. But then, here, attached to that is the derivative of the inside. And I could just write like d dx of 3x squared plus 2. I could just say, like, I'm not going to do that part yet. I'm going to save that for my next step. Or you can jump right in and say, oh, I know the derivative of 3x squared plus 2, and that derivative is 6. And the calculus is done. The rest is just reorganizing it, making it look nice enough to feel good about what we've written. I know that ambiguity might be driving you crazy. Like, hey, go as far as you want. I know. Just tell me exactly how far to go. There really is, like, you can go until there's no parentheses left if you want. But that amount of algebra is not really what we're looking for. What we're kind of looking for is just combining some things that go together, the 3 and the 6 to get to 18. Monomial factors right after that. And then the 3x squared plus 2 squared. I'm good. Okay. That for me is plenty. Plenty. Okay. The simplest form doesn't have to have no parentheses left. Really, we're just trying to put things together that go together, get rid of negative exponents, rational exponents, things like that. Combining like terms, simplifying if you can. Writing them as a single rational function sometimes if you feel like it's something you're comfortable with. You'll see that a lot of times, especially with chain rule stuff, that although writing it as a single rational function can sometimes be tricky, the answer is actually simple. Because a lot of what we'll have are a lot of kind of similar factors and 2x plus 5s or 3x squared plus 2, the x plus 2. A lot of things tend to happen more than once as we kind of work through, especially once we get to trickier and trickier. All right, let's do this one, and then I will let you do h of x and then capital F of x. F of x is ready, g of x is not. Okay, yeah, there's an inside and an outside, but the problem is that outside is not an exponent, or at least not the way it's written. So let's do that instead. Can we write this with a set of parentheses with some stuff inside, and then just like one exponent, like one thing, exponents are best if you can, on the outside? What would that be? Yeah, it's the 1/2. Cool. So 2x plus 5 to the 1/2. And it's written with the power. The big thing that's happening is the power rule. I just need the chain rule because it's more than just x to the 1/2. So I'm good to jump into g prime of x right here. Exponent goes in front. Exponent gets decreased by 1. Remember, first time through, we just leave the inside alone. Okay, whatever that composite function inside, whatever that is just going to stay. And then we'll multiply by the derivative of the inside. And I think the more you say those things in your head as you're doing them, once you do get on your own, I think the easier remembering the chain rule is. Derivative of the outside, leave the inside alone, times the derivative of the inside. Like saying that out loud or in your head. All right, so multiplying by 2 here, because that's the derivative of 2x plus 5. I think we'll help you out a little bit. And then let's put things together that go together, write things a little bit nicer, and feel good about what we're doing. So let's, just like we did with the 3 and the 6, let's multiply constants together if we've got them. How'd we do? Whoa. We have, that's what we said. That's so, you read our minds.
Yes, Miss Wildenburg was very grateful. She said, thank you so much. Aww. And you can keep the bag if you want, like for your kids or something.
Sweet. So let's finish this one, and then you can come grab a snack if you're interested. Put it like, yeah, right there. I'll come around with the bag maybe. Cool. Yeah, awesome. So what happens with the constants? 1/2 times 2. Goodbye, right? Times 1. Beautiful. So the only thing we have left is the 2x plus 5 to the negative 1/2. Now you can take a step and just write that. 2x plus 5 to the negative 1/2 and then deal with it. Or, feeling good, we can jump right in. Right, negative exponent. So here we are in the bottom of a fraction. So that 2x plus 5 to the negative 1/2 becomes 1 over 2x plus 5 to the positive 1/2, which is the square root of 6. No negative exponents, no rational exponents. No need to rationalize unless you're really feeling like that. It's just not nice. But I'm good right here. This is 198, I think. Top of 198. So chain rule stuff, right? Have an inside and an outside. Let the derivative of the outside kind of take control of what does it look like. If it's an exponent, awesome. I'm going to use that exponent like I would do with the power rule, keep the inside the same, and then multiply by the derivative of the inside. Okay? Then whatever simplification looks good, feels good, is good. All right, go ahead. Try the next one if you're feeling good. I'll leave these up here while I make my way around. Ooh, man, choices. How about this? How about we just start at the top? Anybody like some Smart Food white cheddar popcorn? You make a good point. You make a really good point. Let's get the smorgasbord going here. Let's see. All right. We got popcorn. We've got little bites. All right, hold on. We're going to have a bit of some barbecue chips. So here, we'll do the extras. Okay, and we've got Pringles times 2. We've got Cheetos. We've got Lay's, sour cream and onion. We've got Cool Ranch. We've got nacho cheese. Original Ruffles. Another round of puffs. We got double puffs. We got double Lay's. We got double Ruffles. Original classic Lay's. Double Doritos. So there we go. So we have double of everything except Takis and Cool Ranch, right? Yeah, I think it's a battle to the death. In the form of rock, paper, scissors. Oh, and one barbecue. One barbecue? There it is. All right. Anybody with a Wish Week shirt gets to go.
Yeah.
Ladies first. Ladies first.
My bad.
If you don't want one, you don't have to come grab one.
Happy breakfast, guys.
Yeah, right.
Honestly,
Any part of a nutritious breakfast. Good? Alright, are you good? Everybody else? Anybody else want anything? I'll hook you up if you're far away. No, what do you think? Pringles, popcorn, Cheetos, barbecue, ranch. We do everything. Okay, barbecue's gone.
I looked at my sister.
You know?
I told him around saying, maybe I'll like that.
BJ, what would you like? Pringles? I don't want to break them. Yeah, that's fast.
I got her.
She's very classic original Ruffles kind
I've
of
been
guy.
late to everyone talking to the work week. And Mr. Weller. That too.
If you want seconds, help yourselves. Thank you, ladies.
Thank you.
You're welcome. All right, go ahead. Try h of x and capital F of x.
Wait, who was taking that great Gatsby book yesterday? Oh, wasn't it H book? Yeah.
Nice. Oh, good. I'm glad you
I
found it.
really thought it was like, all right, I got somewhere to go. Yeah, I really came out there.
Let me know if you need like paper towels as a napkin. I will rip one off and some pretty. Okay. So you don't get Dorito dust on your. You look at my solutions for test number 3. You see Dorito dust.
Okay, so.
Yep.
So
Love it.
yeah, so this
Looks
is the
good.
power rule.
Yes.
And
Big thing
then-
happening here is definitely the power rule. X plus 2 to the 2/3. Yep.
And then is the one correct? Because we just look in the
Yeah,
parentheses.
derivative of just x plus 2. Yep.
So
Good.
the squared doesn't matter.
No, because that is taken care of right here. If you wrote it separately, like, and we could do it, but it's definitely more work. If you wrote it like as x plus 2 squared to the 1/3, the big thing that's happening is the 1/3. And you would leave the inside alone, and then you take the derivative of the inside. But the derivative of the inside would need the chain rule again, right? You drop the 1/3 in front, leave the inside the same, decrease the power by 1, and multiply by the derivative of what's in blue. But this is more than just x to a power. Anytime you've got like an inside and it's more than just x, even if it's just x plus 2, we need the chain rule.
Okay.
So here's a good rule to kind of put in the back of your mind. If you have one set of parentheses, you use the chain rule once. If you have two sets of parentheses, you use the chain rule twice. Yeah. And the bottom two, we're going to do. Yeah. The derivative of what's in red. The derivative of the inside, 6x.
How did you get the 2/3? I'm just
Power over root.
So then where did the? Oh wait, it's not as easy, right? The 1/2. I said it was at 2/3.
Here?
Yeah. So didn't you take it?
Absolutely, right? 1/2 goes in front. Leave the inside alone. Decrease the power by 1. Multiply by the derivative of the inside. Now, 1/2 times 2.
So why didn't you put a 1/2 on the third one? Because isn't there still going to be a 1/2?
No, it's going to be a 2/3. Here, I'll do this next one.
Okay.
I think we're good with the top two. Let's see this last one and this next one in action.
I'm having a stressy in this class.
X plus 2 to the 2/3. Let's not eat our feelings.
If I don't eat, then I'm
That's
gonna
what happens
cry.
at midnight with me. I start eating my feelings as I'm grading tests. Yeah. So 2/3 goes in front, inside stays the same, power gets decreased by 1, and I multiply by the derivative of the inside. But the derivative of the inside is just 1. Doesn't have to be,
Oh, wait, what were we doing?
because the 5 is just a constant. So when I drop this 1/3 in front, I just multiply it by the constant that's there. If it was 5x, we'd have ourselves a whole different scenario. But only one set of parentheses means only chain rule once. 2 sets would be 2, 3 sets would be 3. We'll probably stop at 2 sets of parentheses and do the chain rule twice. We'll see how that plays out here in the next. Can I just do it? We'll work it out together.
You know what? Oh my gosh, I got it right. No. Oh, I forgot to add the 3. It was so close. It's a cute root. Why didn't I not think of that earlier? No, wow, it's so embarrassing. What is fun? Oh no.
Face throw.
I decided to be the very passive aggressive.
Didn't sound very passive.
Just aggressive.
Just aggressive.
Just wait. You know what? No.
So gotta get yourself to there for f prime of x to start. The calculus is done. The rest is just algebraic manipulation to make it look as nice as you need it to be, which for me is not usually more than a step or two when things are simple like this. These are the easy ones. I apologize. Calculus is about to get a whole lot harder. Yeah.
I don't understand the last part of the increment.
Okay. Are we cool with this being x plus 2 to the 2/3? Are we cool with what's in red? Drop the exponent in front, leave the inside the same, decrease the power by 1, multiply by the derivative inside. Okay. So what's like? I'm thinking about like now. Do I need a fraction to represent my answer? Well, fractional coefficient and a negative exponent, absolutely. So the first thing I did is I just kind of made a fraction bar, and then I asked myself, okay, like what goes on top and what goes on bottom? Well, the 2 goes on top and the 3 goes on bottom, so that's those 2 right there. Now I've got this x plus 2 to the negative 1/3. Negative exponent tells me to move it to the bottom, make it positive when I do that. So what's on the bottom now in my mind is x plus 2 to the positive 1/3. Well, what does a positive 1/3 fraction mean in my exponent? Power over root. X plus 2 with a cube root around. Right, a power of 1. So it's like there's a 1 right there for this one, and a 3 right there for that. Yeah. But raising that to the power of 1 seems kind of silly, so whatever, ignore what's in red, but that's where it's coming from. So I'm going to do the same thing here. I'm going to think like, okay, what's on top and what's on bottom? Okay, cool. So I've got a fraction for sure. Fractional coefficient plus some negative exponents. So what's left on top is what's left on bottom.
Wait, I'm confused. You
I
don't
think
have
so.
to multiply the 5/3 and the 2x together?
You could. You want to call that 10x plus 10 on top? Sure. You want to call it 10/3 x plus 10/3? Geez.
So you do have to multiply to the other 2.
You don't have to.
Oh, I know, but like if you were
You
to do
certainly could.
that. Okay.
You certainly could. You could also like just pulled out the 2 and called it like 10 times x plus 1. So I think there's some freedom here in how much you choose to expand. Which and like I've said before, I know that lack of concrete, like here's step Z in my process of A through Z. No, you can end at like L or M or you can go as far as you feel like
That's so hard when you're leaving.
I know.
So
It's like,
indecisive.
give me the, like, tell me what things are gonna look like.
Oh.
Um,
This is calculus, right? Not algebra.
So would this be an acceptable answer? If, no. Thank you, Ashley. Right.
no, because we're the X plus 2. The 2X plus 2.
I'm not.
Oh, I see them separated. Okay. Sure. I don't know that that's preferred because you've got like two fractions separated, but I'd give you full credit. I would wonder why you chose to do it that way because like one fraction rather than two sounds better to me. And I think that's why, like, along the way, they've been like, let's practice writing things as a single rational function, because now that things get kind of messy and nasty, it's a little bit nicer. And you'll see when we start working through page 199, actually, like these messy chain rule problems, when we do make them a single rational function, actually look nicer. Sometimes we can get like, maybe we have like square roots all over the place, and by creating a single rational function, I might be able to just have like one square root just on top or just on bottom. So yeah, that's good. If it's correct, if you've done the chain rule correctly and done something to simplify, you're gonna get full. I care about the chain rule being applied correctly. That's my most important thing that I'm looking for here. Product rule, quotient rule, chain rule. That's what I'm testing you on next week. When I send you home with your quiz on Monday. That's what I'm thinking. Yeah. So she distributed but separated. So she multiplied the 5/3 into here.
Yeah.
And then multiplied those fractions into there.
Oh, that's like, can you show like how would you write it if I were to do the 5/3 and 2x plus 2? Like I'm sorry. I don't think I'm gonna know when to stop. That's why I have to look. Okay.
That way was so much easier. I don't know what
Okay, that makes sense.
But then she did this times that and this times that, and just like created just two fractions. 10x over 3 cube root of blah 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 plus 10 over 3 cube root of blah. But I think what's in red is probably, or I mean you could expand this, sure. 10x plus 10. That's not too bad. All right, I'm not done. We are not done. I'll go this way. Still G of X. Last two, bottom of 198. Last two, bottom of 198. Clearly, I don't really have like an inside and an outside yet. And so you see how I start thinking about it is I want to create like the big outside idea and then figure out what's left inside. Now, maybe it would be helpful to look. We didn't do a regular sine square. Yeah, chain rule. Oh, we did. Yeah. There it is. Bottom of page 197. We had sine squared theta. Right, and so we kind of took a second and said, oh, well, sine squared of theta is just notation. What that really meant was sine of theta squared, right? So same thing here, cosine squared of 3x. What are we going to put on the outside? Like, what's really happening here? Yeah, the squared part, right? That's a 2. So what's left on the inside? Cosine of what? More than just x. It's cosine of how many sets of parentheses we have? So how many times do we have to do the chain rule?
What?
Okay, now we work from the outside in. Dos rulos de chinos. Let's do it. G prime of x. Why the capitalization? I don't know. But we're going to roll with it. Okay. Big thing that's happening here is that squared on the outside. So I use the power rule and I leave the inside alone. Okay. I'll see what the color scheme is as best I can here. So blue, right? 2, leave it alone. Decrease the power by 1. I'm just putting the 1. You don't have to, but just so you see that that's kind of what I'm thinking here. And then the inside, I just leave alone. Cosine of, but then times exactly right. The derivative of the inside. Well, I'm just like one layer in, right? We're like kind of peeling back the onion here. One layer in is just cosine of something. And so when I find the derivative of the inside, again, I could write right here like ddx of cosine of 3x. That's what I'm going to do. I'm going to find the derivative with respect to x of the inside. Or I can just kind of jump right in. And if you're cool with it, we'll just jump right in. The derivative, I'm going to put parentheses. The derivative of the inside is negative sine of whatever. The problem, and I'm going to close that off for the derivative. The problem is that what's inside is more than just x or more than just theta. So now we multiply by the derivative of the inside. So there's the chain rule twice. Derivative of the outside, leave the inside alone. Times derivative of the inside. That derivative of the inside leaves the chain rule.
I like over.
Yeah. All connected by multiplication. Yep. Yeah, the chain rule, no matter how many times we did it, derivative of the outside, leave the inside alone. Times the derivative of the inside, leave the inner inside alone. Times the derivative of the inside, leave the inner inside alone. Like we could, it goes and goes and goes. It is a chain.
Over derivatives.
Now we just put stuff together that goes together. Constants out front. Monomial like x powers would come next and then trig at the end. Looks to me like -6. 2 times -1 times 3, so -6. And it goes cosine, sine, whatever order feels good is fine with me. I usually just stick with the order from left to right so I don't miss anything, but it's multiplication, so that's commutative, so you can kind of put them in whatever order you want. Put the dots for multiplication if it's something you like to do. Don't if you don't. I'm good. Pythagorean identities are going to come into play, but I'm not going to stress that part of this. To me, I'm seeing that same one that we saw yesterday with the 2 sine of x cosine of x being sine of 2x, because I've got a coefficient that's a multiple of 2, and then sine cosine. But it goes back to something that you'll see more next year, whether you do AB or BC, or if you take Calc 1 or something like that, where we would have to do what's called U substitution, where I let U equal like the inside. And then I can start like kind of like imagining what that would really be. All right, well, it's not really 2 sine x cosine x, it's 2 sine U cosine U, which would be then sine of 2u. And once you start getting deeper and deeper into calculus, what you'll notice is that U substitution will allow you to use some of these rules way fast and kind of shortens a lot of your work. And it actually allows us to do things that we wouldn't otherwise be able to. So having that ability to kind of like find the big outside and then kind of work your way inside, I think is going to be worthwhile. H of x is going to work out exactly the same, okay? I want to leave that to you to do another time because I do want to turn the page and at least preview where this can take us, if you're okay with that. This would be just sine of 2x plus 1, right, on the inside, and the squared on the outside. 2 drops in front, sine of 2x plus 1 times below. So same exact kind of style here. But let's turn the page. We now know the big three. And basically, the first half of this chapter is now done. Second half, you'll see it's really just learning some exponential and log rules for derivatives, which are really, really cool. And it gets into some things that are really, really nice. That's just going to be more of a, like, here's the rule. Let's see if we can apply it. Logs and exponentials, all that stuff kind of going together. But I think messing with some of these trickier ones is a little bit more worth our time today and Monday. So we got product, quotient, and chain. We can use them, like 2 of them or all 3 of them within one derivative. But the thing that we'll want to try to do is figure out what, and I keep saying it, so hopefully this, like, what's the big thing that's happening? Like when I think about like rewriting f of x so that I can find the derivative, is the big thing happening a product? Is the big thing happening a quotient? Or is the big thing happening like the chain rule? And then I start incorporating different pieces as I go. Yeah, like this is, okay, 5x. Again, you can always pull a constant out and just multiply your ending derivative by the 5. Like the derivative of f of x is really like 5 times the derivative of all the stuff without the 5 in it, right? X times square root of x plus 3. But how should we write that square root of x plus 3? To the 1/2. Cool. And hopefully you can see that kind of like the big thing that's happening is this multiplication of those 2 different numbers. And so if you can imagine what that main thing that's tying multiple functions together is, sometimes it's the chain rule because it's composition, sometimes it's quotient or whatever. If the big thing happening here is the product, and the big rule that we're going to follow is going to be the product rule. But within that, you can see, okay, u is 5x. Let's do that. So u, 5x. So sweet, du, pretty easy. That's just going to be 5. But if v has a power, but the base for that exponent is more than just x, what are we going to need just to find dv? The chain rule. Okay, so part of what we do within the product rule actually needs the chain rule, where we drop the exponent in front, we leave the inside alone, we decrease the power by 1, and then we multiply by the derivative of the inside. Thank goodness that derivative is at least just 1. So this isn't too crazy. But this will be our last one that we look at, just to kind of get you in the mode. Okay, now I'm gonna pause for a second so you can see. Right? Look at g of x just briefly, right? The big thing that's happening is sine, right? What's the outside, right? It's sine of some stuff. But it's not just sine of x. It's sine of more than that. So I'm going to need the chain rule to do that. That's the big application here, is the chain rule is in motion. But to find the derivative of the inside, what are we going to need to do that? The quotient rule, right? The big thing that's happening on this next page is a fraction, right? This is h of x, the big kind of tying things together piece is a quotient. So I'll use the quotient rule for sure, v du minus. But when I find du up top, what square root of 2x plus 5, right? 2x plus 5 to the 1/2. I'm gonna need the chain rule. So that's kind of the mixture that we're looking for. But let's do this one and then we'll call it a day. Okay, so again, the big thing that's happening is the product rule. So I set up my little u's and v's, and I can jump right in right away. U dv. I'm going to write it just so that we know, kind of looking back at this, what the big idea was. I want the big idea. Wow. Sorry, my weird Friday mood today. Here we go. 5x. I'm going to put parentheses and keep myself super safe. dv. Now, I'm going to simplify at least a little bit, like multiplying by 1 doesn't change anything. So I'm just going to drop the times 1 part of that. That's the negative 1/2 up there. But I'm going to leave like negative exponents. I'm going to leave fractional exponents. I'm going to kind of see what happens as we go. You'll see that as we mess with different applications of chain and product and quotient rule stuff, sometimes sometimes we've got lots of common factors that we can add and subtract and put together. So I like to leave them in this form as long as I can and see if I get lucky. And sometimes we can, sometimes we can't. UdV plus V du, and simplify that. Now it's really just like monomial times a monomial, because it's something to the 1/2 monomial. So not a whole lot of distribution that's happening here. This just becomes 5/2 x. I'm going to go super slow. X plus 3 to the -1/2. I'm just going to combine things that I can, put things in a nice order, and then choose what kind of simplifying I think I would like. Now, we could have right away, like with that first product, like done 5x over 2 square root of x plus 3. And you could jump right to there if you want, for sure. Same thing with the second one. 5 square root of x plus 3. You can make that change early. But that might hinder some of the things that do come up. But you're okay to do that. I like to take my time, slow down a little bit, and see what I can do and see if it works out. Because what you might notice early on is what's in common. And factoring might be a best way to get some of the rationalizing and simplifying and stuff out of the way. Do you notice anything that's in common? X plus 3. So we have a common base there, which means I can pull that out. I'm also going to pull the 5 out as well. Now, when we pull out what's in common, I can't take more than I've got. And when I factor, I'm looking for the smallest exponent. Right? Common factor between x squared and x to the 5th is x squared. Common factor between x plus 3 to the -1/2 and x plus 3 to the 1/2 is x plus 3 to the -1/2. And then I just see what I have left. Now, this is one way to do this. There's plenty of other ways to do this. I see what I have left in each one. I've got an x over 2 or a 1/2 times x, whichever one you want. And that's it, right? Because I took the 5, I took the x plus 3 to the -1/2. Plus, well, I took a -1/2 from a 1/2. Right? If you take x squared, give me like 30 extra seconds here. When you take x squared from x to the 5th, we would have x to the 3rd left, right? The difference between those exponents. So what's the difference between these two exponents? 1. Just x plus 3 to the 1st. Kind of crazy, right? But it actually allows us to combine things together. I'm going to let you go right here, right? Because that x plus 3, I don't even need the parentheses anymore because it's just raised to the 1/2. The difference will always be 1 between those two. Always, 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 because what did we do? We subtracted 1 from the next one. And having that kind of knowledge ahead of time, I think is going to help us, because we're going to keep going. We'll pick this up right here on Monday. We'll keep going and see what happens. We'll be able to take some x over 2's, which maybe we might like to see as 1/2 x, and combine some stuff. Have a great weekend, everybody. I will see you Monday. Nothing you need to do for me for this weekend. Thanks. Yeah.
How did you get the times 1 for dv? Like, where does that
The derivative of the inside is 1. Derivative of x plus 3 is just 1. That number right there. Thanks, see ya. Is 1.
So it's not like the regular like dv where you just take like 1/2 x to -1/2. It's like we do the.
It's the chain rule just to find dv because it was more than just x being raised to the power. Now, because it was just x plus 3, it doesn't change very much. But if that was like 2x plus 3, then I'd be multiplying by 2. If that was like x to the 3rd plus 3x squared plus 5x plus 7 to the -1/2, right? Then I'd have the derivative of all that craziness on the inside being multiplied through the end.
Okay. Okay.
Right?
Yeah.
Derivative of the outside, leave the inside alone, times the derivative of the inside, whatever it is. The inside is just x plus 3. The derivative of that I multiply by is not very tricky. Maybe some colors. Inside and blue. Right? Big thing on the outside is the 1/2. Right? That's kind of the big thing. That's how we use that power. Drop the 1/2 in front, leave the inside the same, increase the power by 1. But then I multiply by the derivative. The derivative of what's in blue is just. Cool.
Okay, yeah, the colors help.
We'll practice some more on Monday. This is when it starts getting tricky.